first speaker this morning is Yiwei She, Colombia. I shall talk about the unpolarized Shafarevich conjecture.
Okay, thanks for the invitation. Can everybody hear me? Great. So for this entire talk, I'm going to fix a number field and a finite set of its places. Which just means primes in the ring of integers of k. And also, I'm going to, whenever I say isomorphism, it always means isomorphism over k. And the theorem that I want to talk about today is the following. So the set of K3 surfaces defined over K and with good reduction over at primes outside of S, so is finite. And so just a bit of notation. I'm going to denote such things by x over k comma s. And this means that x is a scheme over k with good reduction outside. And I should just say, since I guess you guys are algebraic geometers, good reduction means. What?
You're also.
I am an algebraic geometer. Okay. I'll still say what good reduction means. Good reduction at C just means that there exists a model over the ring of the local ring at this place, which is smooth. And so the whose generic fiber is what you started with. So let me give some background for this theorem. The story starts a long time ago with a theorem by Hermite and Minkowski, and it says that the set of dimension 0 schemes over k with good reduction outside S is finite. So this is. So what does this mean? This just says that if you fix a number field and you look at extensions of the field which are unramified outside a finite set of primes, then that set is finite. And you also need to fix a degree of the number field.
What's this theorem?
0D.
Oh, 0D.
Yeah, theorem 0 for dimension 0. Okay, in dimension 1, we also know everything. And for this theorem, you want to fix AGNES, and this is due to Falkings. And it says that if you fix AGNES bigger than 1, then the set of curves which are defined over your field, and have good reduction away from your set of primes is finite. And this theorem really comes from another theorem of faultings, and this is G-dimensional, but it's only for abelian varieties, and you also want to fix a degree. And it states that the set of abelian varieties, okay, so let me fix two integers, so the dimension and the degree, then the set of abelian varieties over your field with good reduction outside your set of places. Yeah, so abelian varieties of dimension and admitting a polarization a certain degree, that this set is finite. So you might ask, like, why do we care about any of these finiteness theorems? And I think the answer is that you care about this theorem because it is a big step in proving the Mordell conjecture. And I don't have time to go into that here, but you can Google Mordell conjecture if you're curious. Okay, so after you prove, or after Faultings proved this theorem, people did wonder, since there are just a countable family of abelian varieties, one given by each degree, if you put them all together, you still get finite even. And it was, I think, a little bit of a surprise when Zarman proved, I guess this would just be theorem G, when Zarman proved that the answer is that there's still only finite dimension, even as you vary the degrees. Theorem. So the theorem is that if I take the union, so let me give this set a name. We'll call it the Shafarevich set of abelian varieties for this data. So if I take the union, that this is finite. Okay. So I guess the theorem I want to talk about today is basically the analog of Zarman's theorem for K3 surfaces. So let me briefly introduce K3s. So first of all, what is a K3 surface? A smooth. Yes.
Zarman's theorem basically equal to Faulting's theorem plus finiteness that touching classes.
No.
So why could you not say, okay, take your abelian variety is exogenous to the
Not over. So that would be true over. I mean,
that I thought
algebraic. That's not rational.
That's
Yeah. Yes. So a smooth, proper surface is in algebraic K3 if, first of all, its canonical bundle is trivial, and we have a vanishing of this cohomology group, okay, and the algebraic means that X admits some polarization, which is just an ample class in the Picard group. So we know quite a bit about K3 surfaces. So let's briefly say what we know. And for this part, I'm going to switch to C because it's much easier to state. So over C. This board will be over C. So the Hodge diamond, this part doesn't need to be over C. We know the Hodge diamond. It's equal to this. It's relatively small. So here you see the triviality of the canonical bundle. And here you see the vanishing of the cohomology. This is just definition. Or is, okay, it's one of these two. Oh. Okay. We also have a Torelli theorem for K3s. So let me introduce some notation. So let omega inside this, so be a generator inside this one-dimensional space. So I'm going to take a global 2 form. Then integration against omega defines a map. So it defines a map from the Betty homology of X. So this is all okay since we're over C. So it defines a linear map on the Betty cohomology of X. And this whole thing, well, what is it? It's a class inside the cohomology of X with complex coefficients. Okay, and we're going to call this class tau. Okay, and the theorem by so the Torelli theorem is, it should look familiar to the Torelli theorem for curves. The theorem is due to Piatetsky, Shapiro, and Shafarevich is the following. So let X and Y be two algebraic K3s over C. Then they are isomorphic if and only if there exists an isometry, so between their cohomologies, taking their periods together. And also takes the polarization of one together.
I'm sitting very close, but I'm sure you will.
Oh, am I small? Okay. And okay. Right. do we know? Well, we know the analog of Falking's theorem. So this is to Andre. I haven't written any dates here, but so I guess so. This is 96, and that was 83. So which says that. So Andre says that the set. So it's exactly Falking's theorem where you put A3 for abelian variety. Okay, so we want to show that despite the countably infinite family of families of K3 surfaces, there are still only finitely many. So the first thing you notice is that if you have a K3 with higher Picard rank, then you can always choose bigger and bigger polarizations, primitive polarizations. You can't avoid this problem. So to prove this theorem, what we need to do is look at all polarizations to try to find a small one. And once you're looking at all polarizations, you might as well as look at all line bundles. So we want to show that any surface, so let's call this okay, so if I write Shaw K3, you all know what I mean. So if I take any surface in our set, we want to show that that it admits a polarization of bounded degree. So this is just some constant. Okay, so recall the Picard lattice. So the Picard group is equal to, so it's the abelian group of line bundles on X. So for K3s, the component of the identity, the kinetic component of the identity is trivial. So this is for K3s only. And there's also no torsion. So we know that it's actually just a lattice. So Picard is a finitely generated Z module torsion field. And since the classes are algebraic, it embeds since the classes are algebraic, it embeds inside the 1-1 classes of Betty. So this is given by the term. Okay, so what we have is that the rank of the card is bounded. Yeah, it's bounded by 22, but yeah, okay. And the other invariant. So the rest of this talk is going to be about more or less bounding the discriminant of this lattice, after which you will know that you get just finitely many isomorphism classes of lattices, and from there you can use more tricks about K3s to bound the polarization. So need to bound discriminant. Okay, so how do we do that? So step one. So the main tool is the theorem of Fulton's, which is kind of why Andre's theorem looks so close to it. So what we can do is, so given something in our set, we can associate to x an abelian variety. And this abelian variety will also be defined over the number field. And it will also have good reduction outside the set of lines. So this is a construction due to Fugger's copy. And then, so this is over C. And I'll come back to the step, so I'll assign credit then.
That's the G, parameter G.
Yes, sorry, oh yeah, so G is 2 to the 25, and D is also 2 to the 25, and this 25 is it's 20 plus 5, is 22 minus 2 plus 5. Okay. Okay. And this abelian variety is going to have a property, and this is the same 25.
What is 5? What is 5 mean?
5. Oh, yes. You'll see 5 later.
And it's 25 equal to 25.
Yes, these are the same 25s. Right. Right, okay, so this abelian variety has some nice properties. What it has is that we can embed the primitive cohomology of our K3 in, well, okay, so first of all, what is this? It's the orthogonal complement of the polarization class of X inside inside the H2. So we can embed this inside a bigger lattice. So L is a bigger lattice. Oh no, I forgot something. Okay, we'll come back. So L is a fixed lattice. I can tell you what it is. It's this one, and you'll. Okay, so here's 5. 5. And this L is what embeds into my my Kugas-Taki abelian variety, which I will write large. Can people see this part of the word? Okay, so this embeds inside the endomorphism algebra. and so let me just explain a little bit about this lattice. I forgot to say that, so the Betti cohomology of X, it has an intersection pairing given by point rate duality, and we know that, so first of all, is and we can surprisingly compute what it is. So it's isomorphic to 2 copies of E8 plus 3 copies of the hyperbolic plane. These are not mysterious lattices. So this is 8 by 8. Great. Okay, so step 2 is to recover this discriminant of Picard from the abelian writing. So Faulting tells us that the set of A's is finite. So it would be great if we can do this. So unfortunately, we haven't embedded Picard inside our abelian writing. We threw away the polarization, which is kind of what we're after. But what we have embedded is the transcendental lattice, and this is equal to the, so it's the orthogonal complement of Picard. And this is what we're going to get back. So why would this help us? Well, it turns out that if you have 2 sublattices that sum up to a bigger lattice, which is unimodular, then you have this equality of discriminants. So the discriminant of transcendental is equal to just the cardinality of the set is equal to the discriminant of Picard. So you need that both of these are primitive, and that this thing, the bigger thing, is unimodular. So from step 1, you get this conclusion. So now I'm going to be a little murky about what type of cohomology theory I mean. So I hope that you will add in the correct one. So what we can do is, so it turns out, you'll see from the construction later on that the lattice L can be recovered from the abelian writing itself. And then to recover transcendental inside the primitive cohomology, we need to know 2 things. One, that the orthogonal complement of the primitive lattice, the primitive cohomology inside L, so has trivial Galois action. So is trivial as a Galois representation. So here I should really put L. And 2, that everything inside the primitive cohomology, which is Galois fixed, is equal is equal to Picard. Okay, and this is also known as the Tate conjecture for K3 surfaces. So once you know those two facts, it's pretty simple to get the transcendental lattice back. You take L, and you take Galois invariance, and then you take the orthogonal complement, and this gives you the transcendental lattice of these. So now we have step 3. So far we have produced a set of lattices that tells you that if you have a K3 that has good reduction, then it has a Picard lattice that's one of these. I mean, it has discriminant bounded by. The Picard lattice has bounded discriminant and therefore is one of these finitely many lattices. So step 3, fix a lattice. So step 3 is showing that once you have a certain lattice that you can bound the polarizations. Yes?
I'm sorry, something on the left-hand side is there a sign issue there?
There probably is. So I think, so the K3 is mostly negative, and this one is mostly positive.
So maybe we want to switch the sign of the cohomology, or?
I do. So globally, so the Kugasaki construction is going to use the negative sign as the naturally occurring one, but that doesn't affect so much.
And then do you need 5 plus 1s, or can you get 5 or 4 plus 1s, or?
No, I need 5 plus
You need
1s.
5.
Yeah, I need it to be primitive, so I need 1 more than 4. So fix a lattice and let so I'm going to define a constant. So this will be the minimum among all vectors in the lattice, such that they're positive, and whenever I have a -2 class, it intersects this vector in a non-zero number of, intersections. Okay, and the claim is that if X has if X has Picard lattice lambda, then X admits a polarization of degree even.
Just a quick question about number 2. You said that the fixed points of the law are the
Picard.
Picard.
Yes.
This Picard over the base field, so
That's right.
it might be some elements that probably appear on the
So
extension.
Picard is only classes of line bundles defined over these. So I'm being a little sloppy here.
So how do you recover the transcendental?
The transcendental lattice I've defined is also non-standard in that I'm not including the algebraic, the classes that are, yeah. So it's really, the transcendental, I really defined it to be the orthogonal complement of the Picard rational over K. Okay, so the proof of claim. So let me realize minimum. Then Feynman's criterion tells you that V is a polarization if so if it's positive, which we have, and every effective class has a strictly positive intersection. So Riemann-Roch tells us that effective classes so effective integral classes are at least -2 curves. So this gives us 3 possibilities. So the class can be it can be 0, it can have self-intersection 0, -1, or -2. We have no -1 curves on a K3. And for 0 self-intersection, you can just break it down into the V component and the orthogonal component. And for the -2 part, we stipulated that it has non-zero intersection. So that all you have to worry about is if this class has negative intersection with V, in which case then you can reflect. Then its reflection across the W plane gives us another vector which has the same length as what we started with, but now it has positive intersection. Okay, so this is not the rigorous proof. I mean, the rigorous proof is you look at the action of the reflection, and you can see that it acts transitively on a set of possible planes. But this is, I mean, it's really what's happening. Okay, so now I should go back to step 1 and construct this abelian series. Okay, I left it out. So first, I'm going to review the classical construction. Which was given by its namesake over C. in the 60s. So what do? So we fix at the beginning a lattice, an integral lattice. So this is a construction that's not only for K3s. Yeah, so I want to negate the signature. And we give ourselves a lattice, and we give ourselves a Hodge structure. Degree 2 Hodge structure. And what we want is an abelian variety. So let me make a definition. We'll say W is equal to the Clifford algebra on L. So what is the Clifford algebra? So this is the universal algebra with a map from the lattice so universals, so B is the algebra, such that multiplication in the algebra is the same as pairing in the lattice. Since this is the first time you've seen this, it's kind of weird, but a good example is the exterior algebra, which is what you get if you take any lattice with the 0 pairing. Okay. And that's on one extreme. If your pairing is semi-simple, then if your pairing is non-degenerate, then your algebra is semi-simple. Okay. So W is just this thing, and so what I can tell you about the abelian variety. So I haven't told you what it is, but I can tell you it's Betty cohomology. And Betty cohomology is just equal to W. Okay?
So V dot V in L is a number, right? So what's the right-hand side?
So the right-hand side, that's a good question. So this is a Z algebra. So there is a copy of Z right inside.
Is that?
So I declare it's actually a scalar. Yeah, it's not just. So right. So the abelian variety. Well, I can also tell you its dimension, which is so this has rank 2 to the rank L. So A has dimension 2 to the rank L minus 1. So let me actually construct it. What we get from the Hodge structure is the following. So let F be the negative definite 2-plane defined by our Hodge structure. And let's give ourselves a basis for it. A standard basis for F. Then the element J, so I'm going to multiply these two basis elements inside the Clifford algebra. Their product has the property that if you square it, it'll be -1. And why is that? Why do you care about that? Well, it gives you a complex structure. So W is the same as Clifford. I write W when I want to think about it as a module over itself. So W has a C action, aka is a C vector space. So WR mod W is a complex torus. Okay, so this is almost an abelian righty. It's missing a polarization. So need to, well, okay, so it has a polarization given by the pairing trace. So we're in algebra, so we can take the trace. Okay, so that constructs an abelian righty. What about the relationship on cohomology? So the classical construction took L to be the primitive cohomology of a K3 surface. So here's the relationship on cohomology. We take W, it's equal to the H1 of our abelian righty. It has two actions. So it has an action of Clifford given by multiplication on the right, and an action given by multiplication on the left. So what this gives you is two maps of Clifford into the endomorphism of the Clifford. So let's look at multiplication on the right. It commutes with, so these actions clearly commute with each other. And I think, maybe I forgot to say, but J is acting by multiplication on the left. Okay, so that means that multiplication on the right of Clifford commutes with the C action. And so these are all actually endomorphisms of the abelian righty itself, not just the H1. Multiplication on the left, on the other hand, well, this is the embedding that I was looking for in step 1. So that's most of step 1, except I did everything over C, and we wanted to talk about an arbitrary number field, and this is where I throw away everything that's comprehensible and say the word Shimura righty a bunch of times. So why don't I do that? Okay, so what is a way too hot structure on L? So this is the same as, so that was due to Kugasaki, and this is due to Deligne. This is the same as a map from the Deligne torus, which, yeah, okay, it's a thing. From this torus to SO of Lattice. So this group is okay. So this group has a universal cover, which is somehow by definition units inside. Well, it sits inside the units of Clifford, which sits inside the just all linear automorphisms of the Clifford algebra. And since it preserves the pairing, it actually lives inside the simplicity of the Clifford algebra with the trace pairing. Okay, and this lift exists. And so this map is the Hodge structure, that the explicit construction of which was given earlier. Okay. So, right. So this formulation magically lets me replace C with, because of all the groups involved are split, with Q. So now I want to put, okay, so now I want to say something about K3s. So recall the Torelli map. Well, it also has a modern formulation. And what that is just that I can take a moduli space of K3s and put it inside, or map it to, rather. So everything here, everything inside this brackets are Shimura data, and everything, so they can get turned into, except for this. So it can get so this is the map. So this is the map, the Torelli map, and the claim is that for all degree of K3s, there is a map from the moduli space of degree depolarized K3s to a single moduli space of abelian varieties. And the construction, as I think Brendan alluded to earlier, is that you can embed all of these lattices inside. So here, I didn't say what LT was before, but it's this one, so every primitive cohomology is isomorphic to this one, and this embeds inside L from step 1. Yeah. The reason I need 5. So D can be written as a sum of 4 squares by Lagrange's theorem. So that's 4. And then since I asked this embedding to be primitive, I write it as 1 plus the sum of 4 squares, which is 5.
This is the replacement for sign.
That's right. Yeah. I think that's the end of the talk.
So if you fix K and S, and look at the K3 surfaces over K with that lines S, do they have any structure? I mean, is there any isogenies or diagonal tools between them?
So I don't know. So you mean isogeny, just isomorphism of the H?
Like the integer of, say, isomorphism in the transdimensional components of the cube, something like that?
And you want isogeny over K? Or I mean, I don't. So for abelian varieties, I don't think you know that. So I wouldn't expect it.
So is there somewhere where the existence of a rational point comes in? Because, for example, even for abelian varieties, you still don't know, even for elliptic curves, you still don't know that there are finitely many genus 1 curves with a given set of bad places. Like that's finiteness of Shafarevich. So is there some? I mean, I guess what you're proving also is that kind of the analogous thing for K3s is also finite. That if you fix a K3 and look at all K3s that are isomorphic to it over the algebraic closure, that that's also finite. And it just seems, maybe that's not surprising from what was already known, but it seems.
Wait. I don't know if I proved what you said.
What was the question? Given a fixed K3, look at K3s that are, say, locally all p-adic places, isomorphic to that first one, and that's your condition. So that seems like that's defined over the same ground field. So that has the same set of bad places. And it's kind of like the analogous Shafarevich group.
But in the case of these 1 curves, you also bound the bad places of the genus 1 curve.
Well, it will be bounded already automatically because it's isomorphic to that first elliptic curve locally everywhere, which has the same places in that direction. So I mean, I'm just saying it's a nice thing that you proved. That it just comes out of this statement.
Oh, okay, thank you.
But it seems surprising. But
I guess, I mean, here, I'm giving myself, instead of a rational point, I'm giving myself a polarization. So, like, I think I'm avoiding the difficulty.
Great.
Genus 1 curve doesn't.
So if I take a fairly simple choice of K and S, like K is the rational number and S is like set 2 or something, can one actually, how hard is it to actually determine the set S that we're talking about? How much of this can be made sort of?
So Falting's
explicit?
theorem is not effective.
Is it? Can you sort of isolate which step or steps of the difficulty?
Falting's theorem.
Okay, but there are cases. I mean, there are some cases where Falting's theorem can be. I mean, where not the proof of Falting's theorem, but
So
one
2
can
to the
classify
25, 2
using
to the
like
25.
Reynolds classification of Falting's theorem.
Say again?
I mean, 2 to the 25 and 2 to the 25. If that were like perfected, then.
Yeah, that's probably each.
Total order.
Just for instance, how much of the conjecture are you actually using?
So I'm using the Tate conjecture over number fields for Tate surfaces.
So this is something that was recent.
No, this was this was written down by Andre in the same paper, I think. But like, it seemed to have been known because Tate, like almost a decade earlier, like said it was an exercise, given some facts.
Any other questions? So Andre also uses Lewis algebra.
That's right. It's almost the same. I mean, you inverse moduli space. Or,
And is it easy to see that you're not introducing in place of the reduction?
yes. Oh, so that, I should have said, that is a new technical result that Andre did not have. So he can make a finite extension to kill some places because he's only working with one polarization at a time. But the part where I get the same field in place is due to very recent work by Kissen and Kuzukara on integral models of the Shimoda. And so the way to get the same places of reduction is that you have a map from the moduli spaces over the integers, I mean, an open subset of integers to the integral model of the Shimura. So you can, it's almost entirely formal. You're saying like I have a point and like an OKB point, and it maps to an OKB point on the Euler.